class we were looking at dithering, and we saw this example, which didn't wow you at all. So maybe now that you've had time to think about dithering, as I'm sure you did over the long weekend, and give another exercise there now, and you can demonstrate to me how the penny has dropped. So here we have 3 colors that are being used to simulate some unavailable color. So color A is 250-20, color B is 210-60, and color C is 0-150. Because of course you can have more than 2 colors in a pattern for dithering as well. Now this pattern is quite regular. So there's, what's going on there? Can you see the pattern that's repeating? So A, B, A, C, A, C, that's the pattern that's repeating there. So there's 3 A's for every 1 B and 2 C's, yeah? So the A and the B and the C are an ratio of 3:1:2. So what's the RGB value of the color that's being simulated? Any takers? I'll even accept really bad answers. Sorry, there are no bad answers, just bad questions, whatever. And it's just trying that counts, you know. It doesn't matter if you're right or wrong. You see, you need a weighted average. Go on, I know you want to say something, Peter. You're just shy. Go on. Yeah, so you need to take the average. It's a weighted average. And so we work with the red first. So considering the red, so there'd be 3 A pixels, so that'd be like 3 times 200, plus there's 1 B, so that's another 200, and then C is 0, and then you divide all that by 6. So it'd be what? 800 divided by 6, yeah? Which is, don't make me do it, or don't make me demonstrate that I can't do it. So 800 divided by 6 is whatever it works out to be at. Is my phone there?
6.
Yeah.
133.
133. Okay, so the red value is 133. The green value then, so you have 50 by 4 plus, sorry, 50 by 3 plus 10 by 1 plus 100 by 2, all divided by 6 is whatever. 43. And then see if you can work out the next one yourselves. So hands up now who hasn't a clue what I'm talking about. Okay, hands up who has half a clue. Well, okay, hands up who has half a clue what I'm talking about then. Okay, right. So let's go back to this here. So in this chessboard pattern, you've got 1 light blue and 1 dark blue. And the light boxes, the light pixels have this RGB value, and the dark pixels have this RGB value. And when you come back far enough from that, far enough back so that you don't even see the pixels anymore, you just get the redness of it is the average redness of those pixels. And the greenness is the average greenness. And the blueness is the average blueness. So you have the average of the red, the average of the green, and the average of the blue. Now, if there was 3 light blue pixels for every 1 dark blue, well, then it would be a bit more complicated. Because to work out the average, you'd have to count the light blue ones 3 times, which is actually kind of what we're doing here, isn't it? Yeah, so in this pattern here, there's 3 dark ones for every 1 light one. So we do the same thing. We work out the average. But of course, we have to count the dark ones 3 times and the light one once. So in this case, when we're working out the red value of these pixels here, the green value, we're working out the green value. The 102 gets counted 3 times. So it's 153 for that light one, then 102 plus 102 plus 102 for the 3 dark ones, and then all divided by 4. It's not straightforward, 1 to 1. Because 1, 2, 1, 2, 3, and then 4. So there's a repeating pattern there of 4 pixels. I have no cursor in this machine. Or you could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dark ones and 4 light ones. If it's not a regularly repeating pattern, as may happen, if it's a bit more random, you might just have to count everything up. But this is a repeating pattern with 3 to 1. 1 light pixel for every 3 dark ones. Here the pattern is more complex. We have 3 A's, 1 B, and 2 C's. So when working out the redness, we have to get the average redness, but we have to count the A's 3 times, so it's 200. So if we go like A, B, A, C, A, C, right? So that pattern there. Well, the A is 200, the B is 200, plus the A is 200, plus 0, plus 200 for the A, plus 0 for the C. So that's the redness of those 6 pixels, and then we divide that by 6 to get the average. Yes, sir?
You can take 4 to repeat the pattern.
Yeah?
Like
A, B,
C, A.
C, A. Right, so I'm completely wrong then. Although I don't think that's why you were confused. But, yeah, so it's actually A, B, C, A, isn't it? A, B, C, A, A, B, C, A, A, B, C, A. Okay, so it's much easier then. Well, just different. Yeah.
The bottom line is only...
Oh yeah, the bottom line is just repeating the pattern again, yes, that's okay. Okay, so it's not 3 A's, 2 C's, and 1 B. It's 2 A's, 1 B, and 1 C. So it's 200 plus 200 plus 0 plus 200, which is 600 divided by 4, which is 150, okay. And then 50 plus 10 plus 100 plus 50 is 210 divided by 4.
52.
Okay, and then we have the A, we have 2 A's, so we've got 40 plus 60 plus 50 is 150, isn't it?
Yeah.
Divided by 4.
47.
Yeah. So I mean, you could, if you really wanted to, actually go into Photoshop and make this, zoom in and actually do the pixels of the colors, and then, copy and paste to repeat the pattern, and then zoom out and see what you get and see if it matches. But so if you were able to do this, my confusing you notwithstanding, then you get dithering. And if you couldn't, I think you don't. Oh, had it all done all right. Okay. How about this one then? Just to really test you. So here we have 3 colors in a dithering pattern, and we're simulating 260-80. So it must all work out to be 260-80. What's Z then? What's the missing color? So here you're like, it's like you are Photoshop. You're trying to simulate 2060-80. You've used 250-20 and 210-60. What's the next color you need now to make this work? So this is a different question now to the last one. If we just consider the red, okay, which is actually very easy if you think of now that I look at it. So if the average redness of these must work out to be 200, and if the X pixels are 200, if the Y pixels have a redness of 200, then what would the Z need to be for it to average out to be 200? Well, 200. So we know that much. The green isn't so easy. So if we need it to be 60, if the X's, of which there are 2, if they're 50 and the Y is 10, then what does Z need to be? Now, what do we know about it without doing the maths? It certainly needs to be higher than 60, because it needs, like the 50 and the 10 are going to average out quite low. So it certainly needs to be higher than 60 to so that it would average out at 60. So the question we're asking is then, and let me say this right, just a sec now, what'd you say? 130. I don't know, we'll see now. So, so 110 plus something, all divided by 4 equals 60. What's the something? What is 130? Okay, very good. Okay, and then next up then, the blue. Do I have it done? Well, I have it done. Here's what I made earlier. That can't be right, what I have here. Anyway, go on. What did I get? 130 and... But it clearly can't be right. Is it 220? 220 is right, yeah? Yeah. Okay. Right, so I don't know if that makes more or less sense, but at least now whether you know whether you know it or not at this stage, which I suppose is something at least. And we'll save this later and go look at this then. Now, so what we're going to look at next now is GIF and how GIF works. GIF stands for Graphics Interchange Format. You will get nerds arguing in the pub about whether it's GIF or GIF. I think the GIF people are right, but there's more of us GIF people. I think the GIF people are actually right though, but you know, screw them and their rightness. Okay, it's just a bit weird, you know. It's only I mean, there's degrees of uber nerd, you know, and the ones that insist on calling it, you know, GIF are special. No. Okay. So, run length encoding is a very basic form of compression, which I haven't really discussed very much about compression. But so, how to explain it? The other way, sometimes I know years ago when I was living in Waterford. Anyone from Waterford? Just as well. So there was a taxi company there. It was like 8 3-7s and a 10. You know, like why saying 777 wasn't so hard. But anyway, we have this tendency where we have a repeating pattern, where something occurs a lot. We have a natural tendency, rather than specify it every single time, to just repeat the thing and how many times it occurs. So let's say, I don't know, let's say you had a sequence of slot machine symbols or something, right? And you had like, you know, bell, cherry, lemon, lemon, bell, cherry, cherry, bar, lemon, cherry, bar. And then there was like, you saw there was like lemon, 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 lemon. You might go, the person calling it out might go, there's 10 lemons, you know, and then cherry, cherry, bar, 4, you know, bars, you know, lemon, cherry, and, you know, 7 bars or something. So that's what run length encoding is. Maybe I should just give you the definition, it might actually be easier. So what run length encoding does is it replaces multiple occurrences of an item with the item followed by the number of time it appears. So instead of saying blue, 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 you'd say blue times 4. And instead of going red, 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 you just go like red times 15. Instead of going green, 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 just say there's 20 greens, you know, and get on with it. So that's a very basic form of compression. And that's something that GIF uses. So, now GIF does a few things, but in principle anyway, in reality it's more complex than this. But in principle, it reads the pixels from left to right in the same order we would read them as if we were reading text. And where there's multiple occurrences of the same pixel value, it would just specify that in the number of times it occurs. So GIF is very popular, or was very popular anyway for a long time, for images on the web. Now it only uses 256 colors. So it uses indexed color, 256 colors, and there'd be a lookup table. And the palette of colors can be any palette that you want. And you might use something like Photoshop. If you had an image in RGB and you wanted it in GIF, you'd use Photoshop to pick the colors for you. Or you can specify them, but it's easier to get Photoshop to do that. So you can only have 256 colors at most in a GIF. But as you saw in your, with your assignment 2, 256 colors is sometimes plenty. An interesting feature of GIF is that one color may be transparent, and there's progressive option as well. So we will look at some of those. So this is an interesting example here. If we have two images, A and B, and they're identical, except B is like rotated 90 degrees clockwise. So B is the same as A. If you take A and rotate it 90 degrees, you get B. If these were both coded as GIFs, well, the question is, are they going to be the same size? But I mean, that I'm asking the question obviously means no, they're not. But which would be the big one and which would be the small one? And what I've just said about GIF, which one is the best case scenario and which one's like a worst case scenario? B is smaller. And why? Yeah, so like in B, if you're starting at the top and going at the top left pixel and going all the way across, well, you have a good run at it. There's a fine long run there. So if this image was 200 pixels wide, you know, the first 200 at the top there are all the same. And then you go on to the next line and you get another 200 the same. And in the next line you get another 200 the same. Whereas with image A, you know, every single one is different as you go across from left to right. So A is like a worst case scenario for a GIF, and B is kind of like a best case scenario. Obviously, you know, best case scenario would just be a big huge slab of black. But, you know, apart from that, that's probably as good as it gets for GIF. So you could, if you don't believe me, actually try this in Photoshop just to see how the exact same image, depending on the orientation, would give you different outcomes. No, like I said, in reality, GIF is slightly more complex than I'm portraying it, but that explanation is sufficient for our needs. Now, so run length encoding needs long runs of the same color to be successful. So, you know, if you have a lovely photograph of the forest and there's lovely trees and leaves on the trees, and you know the sky is blue and lots of lovely shades of different grey and white, this sucks for GIF. You know, GIF wants plain, boring expanses of the same color. So it's ideal for you know, say computer-generated graphics or something where there might be expanses of plain color, or it's great for logos and things like that. Now, dithering causes a problem though. You can imagine how if you had lots of plain blue and it's all the same color, and then you decide you're going to generate that shade of blue using dithering, and you're going to have like dark blue, light blue, dark blue, light blue, dark blue, light blue, dark blue, light blue, dark blue, light blue. Well, now you've just messed with the run length encoding mojo there. So dithering can help the image look better at fewer colors, but then it screws up the run length encoding. So all of these things interacting can have an impact on the cost quality trade-off for your file size versus the quality. So dithering is good, but also bad. So you have to see how that interacts there. So sometimes if you reduce the number of colors, you'll make the image smaller, but the dithering then wrecks with the run length encoding, and so it ends up getting big again. So sometimes you don't get the benefits you would like from reducing the number of colors if you use dithering. GIFs can have one transparent color. So the image on the left there around the edge of the cartoon, obviously the image itself is rectangular, but you can see through some parts of it onto the background, whereas the one on the right, you just have that's not transparent there. Now we'll look at transparency again in another class when we go talk about PNGs some more. So just one color though can be transparent, and it's completely transparent. It's 100% transparent or not. So in GIF, a pixel is 100% visible or completely invisible. There's no in between, which is something we've come accustomed to. Progressive coding is a nifty little trick that was very, very useful in the early days of the internet, when you had very slow connections. And what it allowed you to do was it made things seem faster. Images didn't download any faster, but somehow the wait didn't seem as long. And what it did was it allowed you to half see the whole image, rather than at the halfway point, rather than, you know, fully seeing half of it. So it allowed you to half see the thing. So at the halfway point you saw something like this, and eventually then you got the full image. So that's a progressive download. Whereas a regular download, at the halfway point you can fully see half of it. Now it doesn't get there any quicker, but somehow this felt quicker. Now I know for you people in your super fast internet world, images appear to just come instantly. But in the early days you had to actually wait for them to appear before your eyes. And it was slow. So that's what progressive download allows you to do. So GIF allows for that. It does it in quite an interesting way, actually. You would think there'd be lots of hard maths involved, and all it does is it just changes the order of the display of the lines. So it does these ones, and then it might do these ones. And so it would go, you know, every fourth line. And so when it was arriving, it would start off blurry but get better as it went. Now, there were a few problems with GIF. GIF was the main way to transport images on the web. Sorry, I said web. Before the web. Like, there was no web. Okay? So on the internet, GIF was the main way to send pictures. So any images that were being, you know, sent from A to B on the web, and you can imagine, they were all GIFs. And that was hunky-dory until there was a company that had some patents on some technology that was used by GIF. And they either went bust or whatever, or got sold. Anyway, they ended up the patents became someone else's intellectual property. And that company decided, well, hey, you know, we own the patent on this, so if you were using that technology, we'd be expecting some bobs from you. And so they decided that people could display any program that displayed GIFs could do it for free. But if you were encoding GIFs, so if you were writing a program that saved GIFs, then you had to get a license. You had to pay a fee. And so people were upset, as they do when they have something for free and then they're expected to pay for it. So in one of the earlier sort of open source movements was a bunch of people saying, well, screw you then, we'll go away and we'll make our own image format. And there won't be any patents on it, and we can do what we want with it. And that's how we got PNG, which is Portable Network Graphic. So PNG then, on the other hand, is 32 bits per pixel. So it's not just 3 bytes per pixel for RGB, it's actually 4 bytes per pixel, because you've what's called the alpha channel. So you have the red, the green, and the blue, and then you have how visible or invisible the pixel is. So in PNG, a pixel can be, you know, 50% transparent or 25% transparent. In fact, there are 256 degrees of transparency. There's a whole byte for those. So PNGs are huge in terms of file size, not in terms of popularity, because you've got 4 bytes per pixel, which is a lot. So because of that reason, really, I mean, they're great for storing things in high quality, but you don't want to be shipping them around the planet, you know, at 4 bytes a pixel with no compression. Like, just not ideal. So let me see. So what kind of, if we go back to run length encoding, what kinds of images do you think then that GIFs would be good for? What kinds of things have big expanses of color? Well, logos are good. You know, if you take, say, the CIT logo, I mean, if it wasn't for CIT there, you know, those letters in the way, it would be just mostly a big red box on a white background. That's pretty good for GIF. That's a plain color, so the run length encoding can get a nice run at it. If you think about, say, well, what other things might be good for? Where do you have big blobs of plain color generally? I suppose it depends on the background, yeah. Got 15 minutes now to the end of the class. I'm going to make you sit here and think. But cartoons are good as well. You could imagine how if you were coding a cartoon, or I mean, it would depend on the cartoon. I mean, if it was lots of if it was anyway half decent, like and lots of color, it would be different. But if you take, say, I don't know, if you just take even a picture of Bart Simpson. If you have Bart Simpson on a white background, you've got like white, 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 black for the line, and then yellow, 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 and then black for a few pixels, and then white, 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 white again. So for some things, drawings and things, GIF can be very good. GIF will also fare well where there's a small number of colors. It only does 256 colors. If you've got way more than 256 colors in your image, it might not work out so well. If you've got, like the CIT logo, basically, 4 or 5 colors at most, if you're gentle with the transition from the white to the red, it's going to fly through things like that. Okay. So in the next class, we'll look a bit at, I think we're done with GIF. We'll look a bit at PNG and JPEG. So JPEG is quite interesting. And so I'll see you in a few minutes. Enjoy.